Hello everyone, my name is Huda Lamri, and today I'm excited to present to you our work End-to-End Multimodal Representation Learning for Video Dialog. To start, let's first introduce the video dialog task. The goal of the video dialog task is to train an AI agent to answer questions about a dynamic scene presented in a video. For example, here the AI agent is presented with a short video of human performing some tasks. The end user can ask the following questions. What is happening at the beginning of the video? The agent answers, a man is in front of a washing machine. The user asks a follow-up question. What is he doing? The agent answers, he puts several bunches of clothes into the machine. The user asks, after he puts them in the washing machine, what is next? The agent answers, he turns on the machine. And finally, the user asks, did he talk at all during the clip? The agent answers, there was really no other sound, except you could hear him putting the vacuum away. From this example, we can see that for the AI agent to be able to provide an accurate answer for the second question, the agent has to acknowledge that the pronoun he refers to the man mentioned in the previous utterance. And to answer the third question correctly, the agent has to identify the action turns on the machine from the visual features in the video. And for the final question, the agent has to extract the audio information from the video to decide if the man talked in the video or not. The video dialog task represents a challenging multimodal learning problem. For the agent to provide an accurate response, it must ground its responses in the visual data, the audio, and the previous utters. This task has received considerable interest from the community over the past few years. Many models have been proposed and have achieved new state-of-the-art performance records. For example, Lee et al. Represented a pre-trained GPT model that is utilized and extended to learn adjoint audio, visual, and text features by training the model on a multitask learning objectives and introduce the video GPT-2. Also, Lin X et al. Extracted the audio, visual, and textual features, then performed a multimodal fusion in the language space utilizing a pre-trained BERT model. In general, the current approaches largely focus on obtaining a strong textual representation by leveraging pre-trained transformer-based models such as BERT and GPT-2, while the visual features are pre-extracted independently and later combined with these textual embeddings. In this study, we argue that using the visual features that are pre-extracted from frozen 3D CNN networks trained for action recognition without the added knowledge about the corresponding text association, for example, the questions, results in a reduced performance compared to the joint training of both modalities. This limitation was also investigated in the study Revisiting Audio-Visual Scene-Aware Dialogue. The study demonstrated that most models are biased towards the textual information, while the visual features are not contributing substantially toward the performance. Our goal in this work is to address this limited utilization of visual information in the video dialog task by making the models more visually aware. We propose a new framework that combines the 3D CNN network and a transformer-based network into a single visual encoder to extract a more robust semantic representations from the video. These visual features are effectively combined with the text and audio features to generate the best response to the input question. And to provide the model with a generation capability, we employ an autoregressive transformer decoder with a reconstructive objective. These multiple model encoders form one unified framework that is trained end-to-end to generate a strong multimodal representation. More specifically, for the visual data, we sample a sequence of frames at 16 frames per second rate, and we crop them to 224 by 224. Then these sampled frames are fed into a 3D CNN network. We used i3D network pre-trained on ImageNet to extract global average pooled features from different inception blocks such as Mix4 and Mix5. Finally, the visual transformer-based encoder applies the self-attention over the extracted features and generate the final visual embedding. For the textual data, all the input texts, the dialog history, the caption, the question, and the answers are concatenated to form one single long string. All the words in this input string are tokenized using the word piece tokenizer, and the special tokens, classification, and separation tokens are added to the input sequence. The tokens are then fed into a pre-trained BERT encoder to generate the text embedding. For the audio input, the features are first extracted using the pre-trained VGGH network, and similar to the visual features, these were fed into a transformer-based encoder to extract a contextual representation. But unlike the visual features, the audio CNN network was not fine-tuned. Finally, we adapt a cross-attention encoder that fuses the different embeddings and applies cross-attention over them to generate the final joint embedding. We train the model by optimizing for two objective losses introduced in the Unival model, condition masked language modeling loss and a decoder reconstructive loss. For the condition masked language modeling loss, 15% of the input tokens were masked with a special token, and the model is trained to predict the masked tokens conditioned on the joint embeddings. For the decoder reconstructive loss, at each iteration, the decoder receives the joint encoding and generates one answer token that is conditioned on the multimodal fused input and the previous generated word. We evaluated our framework on the audio-visual scene-aware dialog dataset. The dataset consists of dialogues grounded in human-based action videos from Sharit's dataset. In total, there are around 8,000 dialogues for training, 190 for validation, and 180 for testing. For the results, first we report the results for the generative task, where we train a encoder-decoder end-to-end to generate a natural response, and we evaluate a model using the Common Natural Language Generation evaluation metrics. We compare our model with several state-of-the-art models, and as we can see here, our model outperforms these models across the different evaluation metrics. We also trained the model for the retrieval task. In the retrieval task, the model is given the same inputs as the generative task, but the goal is to retrieve the correct answer from a pool of candidate answers by outputting a ranking of the candidate answers based on the similarities between the answers embeddings and the fused input data embeddings. This setting allows for direct evaluation of the encoded modalities without the decoder performance. First, we evaluate the performance of the language encoders. We note that BERT encoder significantly outperforms the LSTM encoder, achieving 19% absolute improvement. We also measure the effect of utilizing different 3D CNN networks to extract the visual representations. We observe that different 3D CNN networks perform comparably. Finally, the model that is jointly fine-tuned on both modalities achieved the best performance across all metrics with 7% in absolute improvement. We also evaluated the effect of the length of the dialogue information. We tested the model performance in the first round, where there were no prior dialogue utters, and in the third round, where there are 2 prior dialogue utters, and in the 5th and the 10th. The results for each round in the AVS test sets are displayed in Table 5. And as we can see from the table, the model performance improved significantly from the first round to the third with a 22% in absolute improvement. However, we see that the model performance dropped in the 5th and in the 10th, as the dialogue tends to become more generic and informative. To conclude, in this paper, we propose a new framework for video dialogue task. In our framework, we optimize the learning from the visual input data by jointly training the visual encoder end-to-end with the different modality encoders like the textual and the audio encoders. We conducted extensive experiments on generative and retrieval tasks, and the results show significant improvement across all tasks and metrics, reinforcing our belief that fine-tuning the video encoder is crucial for the task. For future work, we aim to extend our goal to pre-train our model using self-supervision tasks in raw and labeled data to generate rich contextual multimodal representations that can be used for several tasks such as video captioning and video retrieval. Thank you so much for your time.